we will start with the first lecture as so this. So it depends on the level at which you want to read this. I feel at this level there are some books. My knowledge is old. I don't read books anymore, so you can, if you know better books, you can see, you can tell me. Then there is a University of Cambridge lecture notes online. It's kind of brief, but kind of gives you an idea. Kogut. There are many, I mean, of course, if you want, you should read Weinberg's book, which is always good to read, right? So, fine. So I guess if all of you have done the course on relativity, all of you know why we need to work with special theory of relativity, right? Why do we need special theory? Why are we not happy with Newtonian mechanics? I see nice smiles, but no answers. What happens near about the speed of light? Huh? Mass varies, okay. Anyone, any other explanation? One by one, just kind of.
Doesn't work. Galilean transformation doesn't work.
Doesn't work, okay. What fails, do you know what fails? Light's properties. So let's start with writing, for example. This board is so dark. Are you seeing that better, or would you like to see the board better? You want to see the board better? Are the board lights put Budiyuma? Thank you. Thank you. I think yellow will be very good. Yeah, thank you. Excellent. Okay. Yeah. Okay. Actually, I would like to call it the speed. Yellow is nice? Yellow is nice, nicer than white? Okay, good. So, speed of light. So, this you must have all read. Everyone's heard about Michelson-Morley ether experiment. So, what brings the waves, what carries the waves? So, you want to see that in different directions, if the wave is, if the ether wind was pushing it this way, then you should have seen difference in the speed in this direction versus this direction. You didn't find it, right? So, speed of light is always a constant, and that immediately when you're adding velocity. So, if I am traveling at relativistic speed with respect to some other person who is also at relativistic speeds, and then you add our two velocities, it's going to exceed the speed of light, and that directly comes into contradiction with all the observations, right? And so that is why it only matters when you are at very high speeds which are close to the speed of light. Now, I wrote down somewhere the speed of light. All of you have internet, you can look up Google. Speed of light is now a single number with no decimal places. I hope you know that. It is a fixed number, and that is it. That is the speed of light with no error bar. And can anyone tell me why? You all learned quantum mechanics, right? Is there someone here who hasn't learned quantum mechanics? Anyone who has? Okay, fine. So, how can you allow speed of light to be a fixed number with no error bar on it? Using speed of light as a reference for what? Not for any, it cannot be anything else. I cannot use speed of light for my mass, right? I mean, so. Which one? Specific? Yeah. In terms of? Yeah, everyone is saying that, but which particular thing are you talking about? It is a fundamental constant. C is fixed. But why? I mean, how can you get away with such a thing?
I mean,
You will adjust what? You will adjust the mass, or you will adjust what? What definition will you adjust? Very nice. You will adjust the definition of a meter, right? So you take something, I think it's krypton 86, maybe something else, and so many wavelengths of krypton 86, okay, of a particular frequency, I think some orange red of frequency or something like that, because the frequency is fixed, and then that many wavelengths of it will give you, in vacuum, will give you 1 meter. And you know that, you can write, you know the frequency, that is h nu and equal to hc by lambda, so c is then a number. So lambda in meters is adjusted so that c is whatever the constant number, 299 something something something, which is roughly 3 into 10 power 8 meters per second, right? So the definition of meter has been adjusted so that c is now just a constant. So as far as I am concerned, and if it won't bother you, once in a while I will tell you, it is some constant, I will call it 1. Okay, and this is called natural units, but maybe in today's lecture I will keep c and then slowly I will drop it, so that you will also get used to it. And in quantum mechanics and in quantum field theory, there are 2 natural units, both of them are set equal to 1. These are called natural units, okay. H cross is h by 2 pi, h is Planck's constant. So what is the dimension of h? Dimension, I don't want the number. Angular momentum, very nice, so joule second, right? So these are natural units, and your first homework is to show that h cross c, you will see why it's called natural units. It's 192 point something, but I will be happy if you generate this number as your first homework, okay? And you can see now when we are saying relativistic, what is the velocity? So you would have learned from school onwards, what is the velocity of electron in hydrogen atom according to Bohr model? Not velocity but speed. All forgotten in 12th standard final exam. Roughly, do you remember? Electron in the ground state of hydrogen atom, what is the speed? I will just say V of the electron according to Bohr model, where alpha is fine structure constant. Okay? If you don't remember this, you can go back and look at your textbook all the way from school to college, right? What is the fine structure constant? Does anyone remember the value of it or the definition of it? Okay, it's 1 by 137, and what it is actually is it's proportional to E squared, and the remaining constants depend on what kind of units you use. So for particle physicists, which I am, it is E squared by 4 pi, but it can be h cross c, which for me is 1. So you go and take your best definition, but it is roughly 1 in 100. So is alpha c large or small? Is the speed of the electron in the hydrogen atom ground state orbit according to Bohr, is it a large number or a small number? Comparable to speed of light. How many of you think that it is comparable to speed of light? No one had breakfast because hands are being raised like this. Okay, so how many of you think that it is small? See, it doesn't matter, there is no judgment here. I just want to kind of make it interactive, otherwise you will be thinking of lunch, right? I mean, okay, is it clear? So the main thing is that if you compute this is 3 to 10, let's call it just 10 power 8 meters per second, and this is another 10 power minus 2. So this is like 10 power minus 10 meters per second. Sorry. So what am I doing? Sorry. 10 power 6 meters per second. Okay. And 10 power 6 meters per second is roughly 10 power 6 kilometers per hour. Because there are 3600 seconds and 1000 meters in a kilometer. If you forget again the 3.6, again that is, so you are roughly going at 100,000 kilometers per hour. Is that large or small? Large, right? Compared to like my speed right now, it is very, very, very large, right? So that means if you are looking at atomic, subatomic objects, then the speeds involved are comparable to the speed of light, and therefore special relativity must be involved, otherwise you are going to go wrong, because we have found contradictions. All of you know that there are contradictions, and that these objects do not satisfy Newtonian or what is called actually Galilean mechanics, right? Newtonian mechanics or Galileo principles of classical dynamics, right? Is it okay? So of course, I don't know, so now in MSc you would have learned that actually the electron is not going around and around the nucleus, so there's actually an electron cloud, and you would have learnt about S wave, P wave and stuff like that. So it's actually a wave function and the probability distribution around the origin where you expect the nucleus to be like a point object. But it is convenient to think in these terms, right? I mean, so it's not as though the electron is actually going around with this velocity, but it's a number associated with it, okay? Just to clarify, I mean. So here is where we are looking at, maybe we can use more of the board. So in fact, now that we have talked about since all of you mostly have done a course in special relativity, what is the difference between the old Galilean relativity and the special relativity? Tell me again. You use Lorentz transformation, but what is the fundamental difference between the two? Yeah, so time is absolute in Galilean relativity, right? So there is a notion of an absolute space and there is a notion of absolute time. So we will use this example again and again. Someone is going in a train and I am standing on the embankment looking at the train going past. So these are two inertial frames. So since all of you have done a course in relativity, I am not going to define what is an inertial frame. I will only say that one inertial frame always moves at a constant speed with respect to another inertial frame or even a constant velocity. It can be in any direction, it need not be that they are parallel to each other, right? So what actually is the original inertial frame is self-referential, right? So I am not going to discuss that. There is a big question mark in classical mechanics. I am only going to say that this is what we have. So when I am standing here, I am in some inertial frame, train is going past at constant velocity, so that is another inertial frame. And we are going to use the notation again and again of sigma and sigma prime as the space. Okay? So the person who is on the train is simply standing at the window and watching. He is in sigma prime, but that sigma prime is moving with respect to me and I am in sigma. So sigma prime is moving at a constant velocity v with respect to sigma, and further we are making this assumption that since A, I am bad at drawing and B, I have only a planar board to draw on, I am only going to write 2 dimensions, right? So this is the origin x, y, z of sigma, and I will further assume that at a time t equal to t prime, because all the coordinates of sigma prime are x prime, y prime, z prime, t prime, I will assume that when they are at, when the times match, both coordinates coincide at their origins, and again for simplicity, I will assume that sigma prime is moving with velocity v at some later time, it is somewhere here. Is it clear? So that is the train, sigma prime going past me. Notation is clear to everybody? Fine. And according to Galileo, t and t prime will always be the same because he has a notion of absolute time. Once you have a notion of absolute time, then you know what will happen. That person is at rest in the train, and for me that guy is looking like he is going at a velocity v away from me. So I'll have x is equal to whatever x0 plus vt. If he is going that way, it will be x minus vt. If it will be this way, it will be x plus vt. But t prime will be equal to t. So there is no notion of any different time or a different clock associated with sigma prime. And the moment you think about it, you will realize that this actually is in conflict with the notion that the universe is homogeneous. We believe that the universe is homogeneous and isotropic. I am not going to talk about isotropic here. Okay? So the main consequence of the universe being homogeneous, that's same everywhere. Okay, that means the laws of physics must be the same everywhere. So if you are coming from, I don't know, Trichy maybe, and you do an experiment, then you expect to get the same answer that a person who is doing the experiment in Chennai will have. And anywhere in the universe. It's a very big demand, but that is the demand that you make, right? Once you say that it is homogeneous, then you have no special point in the universe, right? Because for example, if it was not homogeneous, there's a little clump of higher density material here. Then I can have a special system whose origin is always at that clump, and then everything will be different when I am at that particular frame of reference compared to other frames of reference, right? So homogeneity means that I don't have any such special clump of matter anywhere in the universe. On some, whatever scale at which I am looking at the universe, the whole universe is homogeneous. And this homogeneity immediately, as you can see, implies that the laws of physics will be the same. Otherwise, if there's a clump of matter in Trichy, then you will get different value of G when you do your pendulum experiment than a person in Chennai, right? Of course, I mean, you know that Earth is not uniform and that it's a density clump, blah, 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 but we are talking in general, philosophically, right? So because of this, the fact that this indicates to you that there is no special kind of frame, and therefore the laws are the same. It immediately tells you that, after rubbing the board, I will tell you what it tells you, that the relationship between coordinates in two different inertial frames have to have linear transformation laws. That means, if I want to write, so I have now assumed that the whole velocity is only in the x direction, so that is just for simplicity. So I will say that I will write x prime is equal to some coefficient which I don't know, x minus vt. And you can immediately see that k equal to 1 will give me back Galilean relativity, right? So I don't have, for example, an acceleration. Vt, let's take v equal to 0. It's not a non-linear relationship, it has to be only a linear relationship. For example, what will happen if I take the origin x equal to 0? If you say x equal to 0, then the origin of the sigma prime is accelerating with respect to the frame sigma. But these are inertial frames, they cannot accelerate with respect to each other. So this is simply not allowed. So this is encoded by writing a postulate which is a very long postulate, which I will simply condense and say that the laws of physics are same in all inertial frames, right? This is the first postulate of laws of physics, same in all inertial frames. So what do you mean by a postulate? It means something that seems true, you can't prove it, therefore you will simply postulate it until some other theory comes along which proves it to be false, then you give it up and find a new postulate, right? So this is what a postulate means. It seems very reasonable and therefore we will accept it until we find a reason to give it up. And of course the second postulate is what we already talked about, that the speed of light is a constant in all frames. And by the way, we are only talking about vacuum, right? Because all of you have done Maxwell's equations and you know that, or even forget Maxwell's equations, in school you have done refraction and you know that the speed of light changes you do the speed of light in glass by speed of light in the air, you get refractivity. So all in vacuum. The speed of light is constant in all directions, in all inertial frames. So you believe this to be true. It's a postulate because you can't prove it. I mean, you have done an experiment and so you believe it, but there is no theoretical derivation of this fact, so it's a postulate. These are the two postulates of special theory of relativity. And as was already pointed out, it turns out that this gives you the Lorentz transformation equations, and it turns out also that Maxwell's equations are invariant under these transformations. So I have to now do what I call Lorentz transformations. Sorry, since I'm writing big, I'm writing short forms. I think people will not be confused. Okay, and to continue the story of quantum mechanics, it turns out that Newtonian mechanics is not invariant under Lorentz transformations, it's invariant under Galilean transformations, right? And therefore, the puzzle that happened about 125 years ago was I mean, do we have different frames for classical mechanics and electrodynamics, or do we try to unify them into one, which one is correct, which one is wrong? And those were the debates that actually led to Einstein writing. In fact, there's a very small book, I should have written Einstein's book on relativity. I have rubbed it off, but please look at Einstein's. Very small, very conversational, very beautiful, and you can see how he's thinking about things actually. A very small book. It's available on Amazon, you can buy it. So where was I? So it made Einstein think about what is the kind of consistency you're looking for. Okay, and then of course these developments ultimately led to quantum mechanics also, because Schrödinger's equation, this is the 100th year of quantum mechanics, 1925, Heisenberg wrote his matrix mechanics. 1 year later, Schrödinger came up with the formulation which all of us use today, and we know now that in order to make those equations also consistent with special theory of relativity, you have to bring in Dirac equation and the Klein-Gordon equation, and then that led to quantum field theory and to the laws of the universe that we know today. Okay, so that is the story over 100 years in one sentence. But coming back to Lorentz transformation, so I said that how do these laws of physics lead to Lorentz transformation? So the starting point is linearity. So we believe that the transformation between the two frames, I mean, because the others I don't have to write, I mean, they are y prime is equal to y, because I'm just using a simplified this thing, right? And since for the person who's on the train, he is at rest and I am moving with velocity minus v, I should be able to write a relationship which is x is equal to k into x prime, minus of minus v will give you plus t prime, and since we don't know a priori whether the constant of coefficient is the same or not, let us call it k prime. Now what do we want to do? We want to relate, we know now that there is no such thing as absolute time. We have already seen that it conflicts with observation. So we have to now decide a way to tell what will be the time transformation relation. And that we don't know yet, because I know the x prime in terms of x and t, but I don't know the t prime in terms of x and t. So the way to do it is, let me take this equation, stick it in here. So I have x prime is k times k prime x plus k prime v t prime minus vt, that is equal to k prime x prime plus sorry, I want to replace x, right? I want to get t prime in terms of, sorry, I have to replace x prime here, because I want to get t prime in terms of xn. My mistake. Yeah, now you can see that I get right. So now I have two equations. I have x prime in terms of x and t, and I have t prime in terms of x and t. So obviously I should be able to solve it with the given constraint, and this constraint is what leads you to look at a space-time definition of our universe, and that is, again I cannot draw in 4 dimensions, but these are now not x and y anymore, but these are my x, y, z and time. This is my 4-dimensional space-time. Okay. So just like you have 3-dimensional space, what is the property of 3-dimensional space? suppose I just had 3-dimensional space, so let me write x, y and then z, which still I can do for 3 dimensions. And I have a point here which is x, y, z. Then I know the distance of this point from the origin or from any other point, and we write the distance as d squared is equal to x minus 0 squared, or x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Now instead of using x, y, z coordinates, suppose I use r, theta, phi coordinates. I will get some other definition of d squared. But if I take a ruler and measure this length in this frame and in that frame, what will I get? I will get the same answer. So that means d squared is called the invariant. You can see it geometrically. It is an invariant of this space. Now, when I write x, y, z and t as a 4-dimensional space time, so I will write, as I said, here is my x, y, z. I can't now hope to even write 4 dimensions. So this is all x, y, z and t. So any point in this space does not satisfy x squared plus y squared plus z squared plus, I now convert time into a space dimension. Ct has the dimensions of space, but it will not be x squared plus y squared plus z squared plus c squared t squared, but it will have minus c squared t squared, because logically if you look at it, how much time is required for a light beam to go from the origin up to this point x, y, z? It will take a time t, right? And that time t will be exactly the, so Ct or Ct squared will be equal to x squared plus y squared plus z squared, right? So because this is the velocity and it covers a time, distance by time is speed, right? So that is the distance, t is the time, so c squared will just be x squared plus y squared plus z squared by time squared, which means that if I write, instead of d squared, I call the 4-dimensional invariant s squared, I will get s squared is equal to c squared t squared minus x squared minus y squared minus z squared. And if this is 0, it means that light was traveling in time t over a distance x comma y comma z, right? So this is called a light-like particle, object or whatever. If this is greater than 0, that means the time taken is much longer than what light takes. That means this is some object that is more massive, and if it is less than 0, so this is called, time is positive, so it's called time-like, and here the space will be positive, so it is called space-like. And for physical objects, they can only be, Moment's thought will tell you that they can only be light-like or time-like. The more massive it is, the more time-like it is, and causally you can see that space-like objects are not accessible to you. It's outside your, because the time for the light signal to reach there will be longer than you can, because you will already have moved away from that point into the future, right? So that is the point. So this is the starting point. So now let us assume that these transformation laws, we are looking at a light beam, so that means there is a light beam in the train and I am watching it, so then that is moving at the speed of light. So I will take these equations and write in sigma, I have, let's write it this way, x squared plus y squared plus z squared is equal to c squared t squared, and in sigma prime I will have x prime squared plus y prime squared plus z prime squared. And you see what I have used? I have used postulate 2, right? C is the same in all frames. This is the second point where we use it. Now what do I have to do? I have equation 1 for x prime, I have equation 2 for t prime. I will stick it in here, so I will have, this will be some function of x, y prime is a function, is just y, z prime is simply z, and I can write this as also a function of x comma t. This is some function g of x comma t, You can do the algebra. I mean, it's very straightforward. Maybe I should do it on the board, but it's just rearrangement of these things, okay? So what will you get? Because these are squares, you can see that I am going to get t prime squared, for example, will give me some ax plus bt whole squared. So I am going to get x squared, t squared and an xt term. So what will I have here? Let me write here. So my first equation is x squared plus y squared plus z squared minus c squared t squared equal to 0 in sigma, and in the second one I will get some a x squared plus y squared plus z squared plus b t squared plus c xt equal to 0, right? Because when you substitute you will get x squared, t squared, xt, all those terms will come. So what do you have to do? A is equal to 1, b is equal to minus c squared and c is equal to 0. You have to do that. What will you solve for? You will solve for k and k prime. Very standardly you will solve for k and k prime and you will get k is equal to k prime is equal to 1 by root of 1 minus v squared by c squared. You can, maybe if there's a tutorial session you can do it, or you can just take 2 minutes to work it out yourself. Okay, this is the transformation law. Is it clear? So that means if I now write it down nicely here, I will write x prime, and this is now usually called gamma, and let me write gamma of v, x minus vt, and if you substitute all the stuff that I solved for t prime, all this equation which I just rubbed off, I have ct prime is equal to the same gamma v into, or if you want to put the c, and v by c is sometimes called beta. It tells you how, because beta will go from 0 to 1. 0 means it's not traveling, it's at rest, and 1 means it's traveling at velocity c or speed c. Okay? Now the inverse relations. How do you get the inverse relation? Same thing. The reasoning is that he thinks that I'm moving at minus v, right? So I will have simply the same equations with v replaced by y minus v, and now you can see why I put gamma of v. You can see the symmetry which arises because the dependence is as v squared. So gamma is symmetric. This has actually some implication if you look at the group theory of Galilean transformation, but I am not going to go into that. You just write gamma of v over here. There is no gamma of minus v. So it will be x prime plus vt prime, and ct will be same gamma of v. I am not going to write gamma of v anymore. This is simply to tell you that gamma is an even function of v, and it will be ct prime plus vx prime by c. And these are called the Lorentz transformation equations, which I think 2/3 of you have already seen. And towards the end of this lectures, we will actually see that Maxwell's equations are consistent with the Lorentz transformations. You can obviously see that Newtonian dynamics is not, because T is an absolute constant, right? So you will not find any this thing. Okay, so I have written in my notes that this lecture series will not discuss any experiments that led to these developments, but I guess you have realized it by now, so okay. Now that we have the Lorentz transformations, what do we do next? Oh, okay, I have a note on, let me simply write this down. It is very straightforward and you can work it out. A 3-dimensional Lorentz transformation. So we will come back to these 4 vectors maybe in the next or next to next class. So this is in 1 dimension. It was moving only along the x direction. So 3-dimensional Lorentz transformation So same thing, you have to say the same thing, the two frames match at t equal to t prime equal to 0, and it is moving with respect to the other frame by velocity v, etc., and so on and so forth. But now the velocity is the vector v, because it can be in arbitrary direction. So the obvious thing to do is, the frames are moving not parallel to each other in the x direction, but in arbitrary direction. So the first thing you will do is, you will find the components of the vectors which are parallel to and perpendicular to this velocity. So the ones which are parallel to this velocity will behave like the 1D transformation, and the perpendicular ones will not get transformed. So that's all we are going to do, and just let me write them down. So we have, so R parallel is the parallel component of this position vector of x, y, z, is gamma times R parallel minus Vt, and gamma, what will gamma perpendicular be? Sorry, R perpendicular will be, what will happen to the perpendicular component? Exactly, it will stay the same, exactly like this, right? These were the perpendicular components, except they had names of y and z. Now whatever it is, R perpendicular is a two-dimensional vector, right? There are two perpendicular components, they will remain the same. So they will remain as R perpendicular. So I am just writing R this way to distinguish from gamma. I realize it looks the same. And what will T prime be? Can anyone guess? T is of course T. What will happen to this? Sorry, who said that? Can you repeat it? Who is speaking? Can you raise your hand? Yeah, tell me again. No, not x prime. I'm asking this equation. What will be this portion? Very nice. It will be the same, the component parallel to R, right? So it will be V dot R. Okay, if I put a C, then I put a C. Sorry, I might make mistakes in C, because for me C is always 1. So if they don't match dimensionally, please put the C so that it matches dimensionally, okay? Is it okay? Yeah. Because you can see this here. What we have done is we have taken a special case where we label the coordinate system such that the velocity was in the x direction and the perpendicular components did not change, right? Now you can imagine that even though now what has happened is, sorry though I'm very bad at drawing, if this is x and y, now I'm saying that this is in some arbitrary direction, so the frame is moving like this, right? X prime and y prime, right? So it's some arbitrary direction of v. So again, what you do is you make the components parallel and perpendicular, and the two perpendicular components will not see what is called the Lorentz boost at all. This is called the boost, right? So I mean your full proper Lorentz transformations has a boost and the rotation both, right? So these are the boosts. So it will not see the boost at all, right? It will only see only the parallel component will actually get affected, and that will have many physical consequences. We will see that when we do electrodynamics, right? And then this is the messy part which you can do for yourself in some tutorial session or as homework. So this is gamma times R plus, sorry, no gamma, R plus gamma minus 1 into V into R dot V by V squared minus gamma Vt. Just put the parallel and the perpendicular components together, right? And you'll get the full, these are the components, right? You just put them together and you'll get this. So you can just try that as homework, but it doesn't convey anything more than what we already had, right? Now what we will look at, we will sneak in something. I want to leave this here. So this is not interesting, I will leave it. I want to get a velocity law, I will do successive Lorentz transformation. That means I will have sigma to sigma prime to sigma double prime. I'll call this velocity v and I'll call this velocity w. So I'm applying successive Lorentz transformations. Okay, and then after that I will stop and give you some interpretation because we are just looking at equations. Okay. So the first thing is, let's look at this. So the coordinates are x, y, z, t, x prime, t prime, x double prime, t double prime. I guess there is no difficulty with that, right? And then at origins of all coincided at t equal to t prime equal to t double prime equal to 0, right? So see, you must understand, when we say origins match, we can always define the origin of our coordinate system, right? So we choose to define the origin at the point t equal to t prime equal to t double prime equal to 0. And then Einstein will spend an entire chapter, and many people have spent entire chapters on what is the meaning of this. Can you actually synchronize clocks in two different frames? And it leads to a lot of paradoxes, and you can read all about them. Now with Google, you don't need a teacher, you can go and look it all up. So we will only give you Blackboard lectures, and you can look at nice animations online, okay? Fine. So what do you have? What will be the transformation? What will x double prime be? Let us take a simple case, 1D Lorentz transformation, velocity is in the x direction. So w is in the x double prime direction and the same as the x prime direction, okay? And the same as the x direction. They are only 1D Lorentz transform. And if you really are interested in algebra, you can do the general 3D double transformation. Okay, so what is x double prime? Somebody? That's why I didn't rub this off. Gamma of w, correct, very nice, times, very nice, x prime minus w, very nice. And what is t double prime? Yeah, c squared, okay, something will come there, okay? And y double prime is y prime, which will be y, and z double prime. Now what will you write for x prime and y prime? What is x prime in this equation? What is x prime? Very nice, gamma v into x minus vt, right? Minus w gamma v into t minus vx by c squared, right? And this also you can write. What will you get? I think what I would like to do at this point is give you 5 minutes, work it out in your notebook, and somebody tell me what the answer is. We have this double substitution, right? So I just want you to write only for x double prime. Once you know x double prime, t double prime will follow. So I have gamma v gamma w x minus vt minus w times gamma v gamma w into t minus vx by c squared, and so you must combine all the terms, right? So as you keep writing, I will give you hints. Don't substitute for gamma v gamma w. Just simplify the rest of it. I mean, that should just take you 1 minute, right? To just collect the terms. You're just collecting the terms, right? And those of you who have already seen will start to recognize the second term, right? right? Okay, now what you do is this coefficient factor, take the square of the coefficient factor and simplify it. Put it all in the denominator, so this, forget the square root, so it will be 1 minus v squared by c squared into 1 minus w squared by c squared into square of 1 plus vw by c squared. Simplify it and you will get some nice answer. Come on, do it so that you don't fall asleep. And show that the answer for this, let me just write it down. Did everyone get this? I'll wait another minute. It's pretty straightforward, right? Just the denominator. What did the denominator square come out to be? That is this quantity. So what did this quantity come out to be? I square it all and then we can put a square root of it, right? And that all is in the denominator, you can write it in the denominator. The whole thing came out to be 1 minus capital V squared by C squared. That is what is gamma capital V. Did everyone get that? How many of you got it? Okay, I'll give you another minute. Please try. So what I want you to do is gamma V squared, gamma W squared, 1 plus VW by C squared, the whole squared is equal to, or you can write it as, let me write the inverse of this because I know that's what I'm going to get, is 1 minus V squared by C squared, 1 minus W squared by C squared divided by 1 plus VW by C squared, and now you can expand the terms and you will get the answer, right? I want you to try it. It's just a lot of algebra, so you'll feel nice and happy when you get this answer. So you can already see that this structure is here, right? X is here X, T is here T, and V plus W by 1 plus VW by C squared is V. So this whole square bracket is here in this. So this whole thing just reduces to gamma V. That is what I want you to show, right? So what does this look like? I have two successive Lorentz transformations of velocities V and W, and it looks like a single transformation, not of V plus W, which is what Newtonian or Galilean relativity would have given you, but it is the combination V plus W by 1 plus VW by C squared. Is this clear to everybody? If I first push you by V and push you by W, you don't get pushed by V plus W, but actually V plus W by 1 plus VW by C squared. And why is this important? What happens when V and W are both C? What is capital V when V and W are both C? C, right? Capital V is C. So this takes into account the fact that you cannot travel at a speed greater than C. Whatever you do, if the maximum of V and W can only be C, and the sum of the two velocities will be in such a way, they will combine in such a fashion that they will add like this, so that the sum can never exceed, that is the relativistic sum can never exceed C. Okay? So you will not have absurdities like if I am traveling at 1 meter per second and then the light wave is going past me, then I travel at 1 plus C. No, I don't travel like that at all, right? I always travel not more than velocity C with respect to any observer. And no observer travels with respect to me at any velocity greater than C. When I say velocity, I mean speed. So this is one of the major consequences of Lorentz transformations and what is incorporated into the special theory of relativity. Nothing can travel faster than the speed of light. So light-like vectors are the fastest, and therefore I've rubbed it out. Anything, and we will come to that when we talk about mass energy equivalence, which is also Einstein's work, we will show how massive objects can only travel less than the speed of light. And only exactly massless objects like the photon can travel. Photon is a quantum of light, so it will travel at the speed of light. Okay? And nothing can exceed that. Somebody is asking a question? Oh, outside? Okay. Is this fine? So now you see we have got the law of addition of velocities. You could have done it, see there are many ways to derive all these things. You could have started with one velocity and then, with position x prime and then time t prime, and you can define velocity as dx by dt and dx prime by dt prime, and all of them should give you the same answer, okay? Okay. So before going into more of the velocity and acceleration and stuff, let me look at the interpretation of a few things. Gayatri, I can hear you here. I think you're close to some monitor. Yeah, sorry. Yeah. Okay. So some of the consequences of special relativity. So now we come back to clocks. So this we start out with what is the relativity of simultaneity? So what does this mean? Let us assume that some small region delta x around me is essentially the same space-time point as I am, okay? So something is happening in my vicinity, maybe even in this room, okay? So you are saying something and you are saying something at the same time. So we have the notion of two things, two events happening at the same time. So first we define what is an event. When somebody switches on the light and the light beam actually reaches my eye, that is one event, right? Now the time and the position, because now we are talking about relativity of space-time. We will never talk about space without putting a time bar on it, right? Because we know that it is otherwise meaningless, right? So we want to know this event which occurred. We want to know its coordinates, x prime, t prime. There will be a y prime, z prime. When I say x prime, t prime, I mean in some coordinate system. But that the event occurred is not in any doubt. Someone dropped a bomb on Iran is not in any doubt, right? But depending on whether you are on a spaceship somewhere or whether you are in Iran or whether you are in India, the time or the position of course is also not in doubt, but the time at which that event occurred depends on the observer. Two things will be there. I will not talk about the second thing, the time, information to reach from there to here, which cannot be faster than the speed of light. That will lead to something called the Doppler effect. We will talk about it maybe in the third lecture. But even now we have seen that if the two are at different of speeds or different inertial frames with respect to each other, then of course the t prime will not be the same as t. So the event itself is coordinate independent. This is a very important point to understand. Event is coordinate. When I say coordinate, I mean space-time coordinate independent. So an event is an absolute thing that happens. Nobody questions that event has happened. The only question is at what point in space and time do I see it and do you see it? And again, as I said, if we are all in the vicinity of each other, then of course, suppose we are all in this frame now, and I say that something happened, maybe I clap my hands, you clap your hands at the same time, all of you will say that the two events happened simultaneously. Which means that if I am in the same frame as you are, then the t is constant, right? Both of us have the same time interval t. Then if two events happen in the same position x, maybe at time t1 and time t2 on the same clock, then I can say one followed the other or one was simultaneous with the other. So within the frame, this notion of simultaneity is extremely straightforward. So then I say that, as I said, I am not talking about the time that it takes for the light or the information to reach me, but that it happened at the same time because I can account for the time taken for the information to reach me. I can say that if two events happened at x1 and x2, but they are all in the same frame, so I can measure it with a single clock, then I can tell whether those events are simultaneous or not, right? So now I bring in another frame, right? What happens in sigma prime? You now notice, that's why I am trying not to rub out these equations, that the t prime will depend on x, right? That is exactly what we have given up in Newtonian's idea of absolute time, right? The absolute time depends on the space position at which you are putting your clock, and these two are at different positions in sigma, and therefore they will be at different positions x1 prime and x2 prime in sigma prime, and therefore they will be associated with different times t1 prime and t2 prime in sigma prime. So obviously it immediately tells you that something that is simultaneous in one frame need not be simultaneous in the other frame. So this is called the relativity of simultaneity. So when somebody says, oh, simultaneously this happened, I was drinking tea and at that time it happened. No, but for me, you were drinking tea like 10 years before and then something happened, right? Because we are in a different frame and that simultaneity doesn't work out over here, right? So how do you now look at this simultaneity? How do you understand the principle of simultaneity? Okay, so maybe I will postpone the discussion of the clock. So to understand this, first of all, the clock that is there at x1 and x2, even though it is in the same frame sigma, I have to synchronize these clocks. But moving the clock, suppose I say that I take two clocks and I make them perfectly matched. Both of them are showing 12 o'clock, 0 minutes, 0 seconds, 0 microsecond. Then I take one clock from x1 and move it to x2. But depending on the speed at which I move it, already the time has changed, right? So this whole idea of even within the same frame and two positions, how to get the clocks synchronized is some chapters and chapters. I will not take it here. You can do it. There are very interesting ways to do it. For example, you take a radar signal, you point the radar, suppose I want to put the clock there, I send the radar signal there, bring it back, find the time at which I sent it, time at which I got it back, then I know the distance because it travels at the speed of light, then I make the adjustment for that and I tell them, the moment you saw that signal, that time should have been so and so, they will adjust their clock. So all those things can be done. So we will fast forward all that and assume that in frame sigma, the times are the same measured by the all matched synchronized clocks. In sigma prime, the times are matched by same synchronized clocks. Okay, so if those people who are curious can go and look up how this is done, because it's a very, very non-trivial thing. In fact, all of you people who are online and ordering from Swiggy and various things, if you don't make corrections for special theory of relativity, and later on you will learn about general theory of relativity, your whatever burger or your fries will not reach you, will probably go to the neighbor or even maybe in 10 streets away. So these corrections become very, very important when you are doing things using satellite based clocks and location, because GPS depends very, very heavily on Einstein's both theories of relativity. Okay, so it is not simply a kind of a textbook kind of thing, it is something that is actually accounted for in your phones today. Okay, so here we have two clocks. Now you see what happens. So one, we have understood that one consequence is that things which are simultaneous in one frame need not be simultaneous in the other frame, but there is something else. The times themselves, as we can see, because now you had one clock to measure this and now we need two clocks to measure those events, okay? And now you will see immediately that there is a further consequence, and this is the dilation of time. So now we have one clock here. Let us say it keeps going tick, 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 and I have a time interval in frame sigma. Let me call it T2 minus T1. So what will be the time interval in sigma prime? T2 prime minus T1 prime. But what is T2 prime and T1 prime in terms of T2 and T1? Now you see that this clock is a single clock. It is ticking away in one place, x. So this x is the same. Okay? Please think, this is very non-trivial. This is one clock here, but this will be two clocks, because this will be sitting at x2 prime, this will be sitting at x1 prime. Again, you will have to think about how x2 prime and x1 prime can have their clocks synchronized, and it can be done, and so you will proceed to the next step. So then you cancel these two, and so you will find it is equal to gamma times T2 minus T1, so it will be changed by delta T. Now what is the property of gamma? Can everyone see that gamma is always greater than 1? What is the formula for gamma? Gamma is 1 by, so a particle at rest, gamma equal to 1, and when the particle has velocity c, then gamma goes to infinity. So gamma goes from 1 to infinity. So it's always going to boost your time interval. Gamma is always greater than 1. So if the time interval is 1 second here, it will be either 1.1 second or 2 second or 100 seconds. It will always be larger in this frame. Okay? So this is called time dilation, because time becomes larger, and therefore the intervals between these two will be this. Okay? So you can see that delta t prime is always greater than delta t. So the frame in which the clock is at rest, this time it is sigma, because I put it at x and I didn't move it at all, always has the shortest time interval, and that shortest time interval has a name. It is called the proper time, and sometimes it is written as tau. And every other time interval will always be gamma times larger than this. So let me give you an immediate application of this. So I don't want to remove this, let me talk about this. So I don't know how many of you read science news. We have cosmic rays coming from all over the universe and reaching the earth, and these cosmic rays have incredible energy. If you remember, I said 200 MeV Fermi equal to 1, that makes H cross C equal to 1. Nuclear sizes of 1 Fermi are therefore associated with million electron volts of energy. So million electron volts is typically, that's what you will find, binding energy of nucleus you will find to be 7 MeV, 80 MeV, so it's in millions of electron volts, right? Whereas binding energy of atoms, which are 100,000 times larger, will be like 13.6 MeV for hydrogen atom, right? So it will be 100,000 times smaller. So if you look at GeV, it is 1000 times an MeV, and if you look at TeV, it is 1000 times that. And if you look at PeV, it is 1000 times that, and if you look at EeV, it is 1000 times that, and so PeV and EeV energies of cosmic rays have been seen in detectors. So that's huge energy coming in from cosmic rays, are mostly protons, up to iron has been seen, but mostly protons, and these protons come with these enormous energies, hit Earth's atmosphere, which is mostly nitrogen, and then become pions. I hope you've all heard about pions in your nuclear physics courses, and then these will decay to produce something called muons. So muon is a charged particle. It is just a heavier copy of an electron. It's about 200 times heavier. It's about 106 MeV in mass. Okay, and because these particles have such high energies, their velocities are very high. That comes from Heisenberg uncertainty principle. High energies, high velocities. Okay, and then you will find that therefore the particles they decay into, these muons, also come with very high energies. Because they come with very high energies, they are very relativistic, their velocities are very high, which means their gammas are very high. So what is the fact about these cosmic rays? I am talking about cosmic ray muons. At rest, a muon decays. It doesn't matter what it decays into. Let's take a muon, E, nu E, nu mu. It doesn't matter. It decays into electron plus some neutrinos. It doesn't matter what it does. But what I'm interested in here in the special theory of relativity is the lifetime of tau is not the proper time. It is the lifetime of the muon, which is 2.2 microsecond. And and it's moving at light speeds. It's so relativistic, you can think of it as moving with velocity of light, right? And so what is the velocity of light? Velocity of light is 30 centimeters per nanosecond. For me, I can't think of 3 into 10 power 8 meters and all that. Okay, so for microsecond it will be 1000 times that, and into 2 will be 600. So it will be 600 meters. So that means the muon will travel 600 meters and decay. So let us say that it's moving very slowly, say 10 kilometers an hour, or 10 meters per second or something like that, very, very slowly. Then in 600 meters it will decay, because that is the lifetime of the particle. What happens now? It will get boosted, this will get boosted by a factor gamma, because it is coming relativistically with respect to the observer who is stationary on Earth, right? So what will happen? What will become the lifetime? It will become gamma times tau naught, let's call this tau naught, and therefore the particle can travel, instead of 600 meters, it will travel gamma times 600 meters. So if gamma is 10, then it will travel 6 kilometers. If gamma is 20, it will travel 10 kilometers, and the whole height of the atmosphere is about 15 kilometers. So if time dilation did not happen, then the muons which interact as soon as they enter the atmosphere would have all decayed away, and you will never see muons on the surface of the Earth. On the other hand, we see how many muons? We see 1 muon per square meter per second on the surface of the Earth, which is a huge number, right? I mean, aggregated and coming from all directions. So you see that these muons have survived. So this is completely out of scale, the surface of the Earth, and 10 kilometers in height is, let me think of a average density atmosphere. So you can see that anything which has something like 10 gamma, 20 gamma is going to reach the Earth before it decays. So this is one of the evidences for time dilation, and not only the evidence for time dilation, you can do a little bit of simple geometry. The atmosphere is usually taken to be 15 kilometers in height, which means that if you look at it as a function of theta, the angle at which it's entering, when theta is 90, this comes to about 400 kilometers. So that means it is about 30 times longer lengths, right? So that means the energies that you will see in the vertical direction, low energies, they would have all decayed away. You will not see the low energies coming from the horizontal direction. So you can compute, for any of you who is interested, as a function of theta, what is the lowest energy particle that you will see at different angles, and that has been actually observed, and Lorentz transformation for time dilation has actually been verified in muons. So that is a very beautiful example of actually seeing the effects of special theory. So the muons that you would never ever have seen if time dilation did not happen are actually seen, and in fact their distribution depends on the distance they travel through the atmosphere before they reach the Earth. So that is one example of time dilation. Now, just as time dilates, we will look at length contraction. So when time dilates, length contracts. It's a very important reason. I will come to it later. If I forget, please remind me. And also I will come back to this example, because in case I forget, I can also write gamma. We will come to this when we come to some other chapter, when we talk about kinematics and dynamics of moving bodies, when we have a body of mass m with energy E. Okay. So let's just remind me to talk about that later. So this is called the Lorentz Fitzgerald length contraction. So you have to do the same blah blah. Now you have something which is, let us write again. So here so again I have 2 dimensions only, because I can't draw more than that. This is my origin, this is sigma, therefore x and y is sigma. Sigma prime is moving with velocity v with respect to this. Okay, and then I have a fish. This is my fish. I hope you don't mind the fish. And then, so this is x1, and now we know that x1 has no meaning, so I have to put x2, t2. Okay. If I want to measure the length of this fish, then I have to measure the two ends at the same time. Because if I measure say the back end of the fish here, and then after it has moved say 10 kilometers away, I measure the front end, then I will say the fish was 10 kilometers long, which is ridiculous, right? So that means I have to tell the people in x1 and x2, see again and again this notion of time and space, to be very careful about whether something is possible or not in special relativity, right? So in order to measure the length of this fish in this lab frame where it is moving, say maybe with velocity u or whatever, you have to measure x1 and x2, the front end and the back end with a ruler or something like that, but at the same time. So you have to synchronize your clocks, tell your friend who's sitting at x2, now measure it at this time. And then both of you measure it at that time, and then you get its length L, which is x2 minus x1. Okay, but this fish now, I can go to a frame which is moving along with the fish. So when it's moving along with the fish, so let us say this fish is moving at some velocity v, so that now is sigma prime. So that means it is at rest in the frame sigma prime, right? So in the frame sigma prime, my fish will look like this, and it is at rest at x1 prime. Now you see it will be at x1 prime t1 prime and x2 prime t2 prime. Why is it like this? Because we talked about the relativity of simultaneity. The moment x1 is not equal to x2, t1 prime is not equal to t2 prime. And so what happens? There are so many difficulties here. I cannot just measure because I have to now know in advance what is t1 prime and t2 prime to measure x1 prime and x2 prime, blah blah blah. But then you have to think of something logical. This fish is at rest. I can measure it at any time, t1 prime, t2 prime, t3 prime. I can measure the back end and the front end. Since it's at rest, I'll always get the right answer, right? So this is the thing that we have to think about. Now we'll write the equations and see. So what do we have? Obviously, what is x1 prime? By now everyone is tired of writing this equation. See the same t. In the earlier example of time dilation, we had this clock at the same x. For length contraction, we have the fish at the same t, the measurement of the front and the back end. And obviously x2 minus x2 prime is equal to the length L prime. And x2 minus x1 is equal to the length L. And so the length, let's call it L naught, is equal to x2 minus x1. And so we'll find L prime is equal to L naught by gamma. Just do this thing, right? So you can see that gamma is greater than 1, so the length gets contracted because gamma is in the denominator. And by the way, the converse is always true. It doesn't mean that, like if the fish checked my length, and then it would also be contracted with respect to the fish. It's not that in any frame the length gets dilated anywhere. This is reciprocal. It will be divided by gamma in all frames. So if I'm in this rest frame, then the person who is measuring me will always find length contraction, right? Is this right? Of course, there is a long statement about what the fish would think, because the fish will say it's not fair, you're measuring me at different times, right? And he doesn't know that it's at rest, so how do you actually convince the fish? You can think about that. See, there are many paradoxes like this. You understand what I'm saying, right? In this frame, for example, the fish doesn't know whether it's at rest or not, but I know that the fish is moving, so I ensure that I'm measuring both ends at the same time. But now I'm measuring both ends at different times, the fish is complaining, no? How can you measure me at different times and say that this is the correct length? So you have to now find a way to convince the fish. So you can think about it. Okay. So now, okay, I will move this to a different time. I will not talk about this because Doppler effect, I don't think I have time for doing that. I will maybe just quickly tell you something about okay. Should I go over time or not? Maybe maybe I should just stop here because it will I want to do some velocity and velocity transformation laws, and I will not finish in 5 minutes. Okay, let me stop now and ask. So this part that I did, which I decided to do very basic because I wasn't sure what the audience will be. Now the question is, should I take the level up a little bit in the next class onwards, if you think that this is all something that you know, or should I just keep going at this pace? So, see, I don't know your backgrounds, and those who are not very sure of the stuff will never open their mouth. So I would rather err on the cautious side, and if some of you very smart people don't get anything out of my lectures, I don't really mind, okay? But I want to clear, if the bulk of the people think that I can up the level a little, I am willing to up the level a little. It all depends on you. How many of you think that I should just continue at this pace? Okay, how many of you think that I can increase the level from next class onwards? Oh God, it's almost equal. 19, okay. Go ahead at this, okay, he is the vote caster, so okay. Okay, fine, yeah. So we will keep at this pace. I will gradually increase the pace as we go forward, but at least in the first lecture I wanted to make sure everyone is with me because these notions are important because it's a very tricky subject, this one. You have to keep thinking, can I do it, can I actually measure this, can I not? And I really recommend you should read Einstein's book, how clearly he has thought through the whole thing, It's an amazing thing, okay? So you let me know anyway if there are any questions. I think I'll stop now because the derivation is going to take some time. And I hate to leave it in half. I will start it again tomorrow. I don't have any portions to finish, okay? We will just keep going till the lectures finish. But somewhere around the 4th or 5th lecture, I will start Maxwell's equations. So before that, if you don't remember Maxwell's equations, just look it up, okay? Huh.
Where you feel the speed of light is constant.
Why the speed of light is constant?
Yeah, you have any intuition kind of example? It's a
None of us had any intuition until Einstein came up with it, right? There was this whole huge, why were Michelson and Morley's experiments? See, whenever you don't get any result in the lab, your teacher gives you 0, right? This is the famous null experiment where they got no result and they became famous for that. So this is a very, very non-intuitive thing, right? That's why the more you think about it, I think the more paradoxical it seems. But you see there are many ways to look at it. One is of course, if you have not found ether, experimentally that is a practical fact. So you just say there's no ether and therefore it has to be the same in all this thing. But if you look at it through group theory, if you look at it, if you look at it through transformation laws, it will all appear, right? See, the fact that you cannot derive it makes it a postulate. The moment something is a postulate, it means that you cannot derive it. You just feel that this is, everything is consistent when you include this. But you should realize that this was 1905. And even relativistic quantum mechanics only came in, because Dirac finally interpreted his antiparticles by around 1931, right? So 25 years passed. For 25 years, people were struggling to combine quantum mechanics with relativity, right? And that brought up the notion of antiparticles. Even for me, that is a mind-blowing thing, right? How do you think of antiparticles? How did Dirac? I still would like to ask Dirac how you thought of antiparticles. You have one wave equation and you get 4 solutions. Somebody will mark you 0 in the exam, right? But you got 4 solutions for one wave equation and then you find that you're a good physicist, right? So these are all really like amazing discoveries. I think that they are not linear, no? Discoveries are not like linear transformations, that they're not incremental. They're actually, so original and so impactful. Maybe other people have intuition about it, but I think they were hints. I think Maxwell's equations, the correction to the original Ampere's correction, all that, and the fact that electrodynamics and transformation laws in electrodynamics, because Faraday has talked about moving objects, right? And therefore there was already a hint that Galilean relativity may not be sufficient. But to say that the speed of light is a constant in all frames and nothing can exceed it, I think is a real huge step forward from there. I think the same thing about quantum, right? To solve Planck's blackbody, you introduce quantum, and that is a huge step again, right? If you can call those the beginnings of quantum mechanics, right? Put H or H cross over there. So these are all, I think, other people's intuition that we only follow. I don't think it is easy to see. I mean, now, of course, you can see that a lot of consistency checks are there, but that is different from intuition. I don't know. I don't know whether I answered your question, but there are many such examples, right? I mean, that you can see sudden, huge step forward has happened in in physics, many subjects, in mathematics, right? Gödel's theorem, I think, shook the foundations of mathematics. So it's there in all fields.
Like in any medium. So can we say that we can never cross the speed of light? Is it applicable to like in any general medium?
Yes.
So in the Lorentz transformations, we used it for vacuum, so we kept C. So if it is for any medium, we'll
That's what I said. You solve it in school. No, in high school, refractive index of water is 1.33, which means that speed of light is 1.33 times less than in vacuum, right?
So we can replace it C with that values, right? So that's
You don't replace C with that value. It depends on how you can solve Maxwell's equations. You don't need to write refractive index, that is in high school. You can actually solve Maxwell's equations with boundary conditions, match them and get, refractive index is like a average potential effect, right? You can actually solve the whole thing using Maxwell's equations and get the same answer, where you will find that the quantity which you expect to be C will be replaced by C times N, right? I mean, C by N, sorry. So you don't need to call it, you just think of it as a velocity of light, it's a convenience, right? You know that frequency of light and wavelength of light are very different objects because E is equal to h nu, that has never changed. If the energy of if the frequency changes, then the energy is changing and your energy momentum relations have gone for a toss because energy is simply being lost, then when it comes out of the medium it is getting gained, it's all not possible. But lambda can change. And the way lambda changes is by V changing, right? So you write hc by lambda and it becomes hv by lambda. Lambda changes, V changes from C to V so that all your relations, E doesn't change and your energy momentum conservation is not in doubt, right? So all this is adjusted, it's self-adjusted. I mean, I don't have to do anything about it, right? But you must understand that when you come to the dynamics of moving bodies, which is the next paper of Einstein, he talks about how any particle cannot travel faster than light, and the more massive it is, the slower it becomes, that it cannot actually reach light velocities because it is moving at some speed strictly less than c. There is a little bit of technicality over here. When you talk about quantum mechanics, there is no particle anymore, there is a wave function, right? So you only talk about group velocities. Now you can have group velocities, you can have wave velocity and phase velocity. Now it's possible that the phase velocity can exceed c, but the wave velocity will be less than c, so the product cannot exceed c. So that interpretation there becomes a little bit technical, but ultimately that particle as a group, its group velocity, it's where the wave function peaks cannot travel from point x to point y faster than c. Okay, so that if you split it up into wave and phase velocities, individually they can exceed, but not both together, which will mean that the particle has traveled faster than light, right? And people talk about tachyons, but then that tachyonic space will not talk with this space. V greater than C objects will not talk to V less than C objects, so they are different space altogether. Okay.
So, ma'am, when we did addition of velocities, we started off saying, okay, T1 equals T2 and equals 0. So, if I consider that, and let's just take any event that is happening in these two time frames, can I not say that they're simultaneous and that contradicts what we saw for
Sorry, go over your argument again. You had two frames with velocity.
Frames, ma'am. And we said, okay, we can take this to be origin like T1 equals T2 equals 0. Like, we considered both to be the origin, no, ma'am. So, like, T1, T2, both are equal to 0, and then we started off with the velocity.
No, that is simply arbitrary, right? You can put your origin anywhere. See, it's a matter of translation, right? What do you mean by origin? You're just translating that, so suppose your origin was at this point. Now I want to move the origin to that point. It is simply a matter of translation. That I'm always allowed to do, right? Okay. This is vector space algebra, right? In a linear vector space, I can choose my origin and only the vector lengths have meaning, right? That's all we are saying.
So it is not the
it is a convenience, it is not a necessity.
Okay. I thought they like, we are considering the time frames to be equal at that point.
No, yeah, you are, but you can always write, for example, you can always write that t will be equal to some t0 plus tau. So I can always shift it, right? I can shift the time. I can say that, okay, I'm 2 hours, like for example, right now, let us see where Singapore or somebody is already at 2 o'clock and back to work, right, after lunch. or maybe 3 o'clock maybe now for them, okay. So they are shifted by some time, but doesn't mean anything, right? We just know that that is the shift. This is also true in Galilean relativity, right? I can think of two frames related by a rotation, by a translation, by because I can write x prime, so I can write it as some x or some constant something. Then I can have a vt because that is the velocity. Then I can do a rotation of that x because also rotations are allowed in the space. So I can also have some displacement by some d. Okay, then I can do it in 3 dimensions. Then I can say t prime is equal to t plus tau. So 3, 3, 6, 3, 9 and 1, 10. I have a 10-dimensional Galilean symmetry, right? And I have a symmetry group and I can think of transformations on this group. So all that can be done. It's convenient for you to think of the 0 as matching because then your equations will become simpler. But you can always keep adding all these. You can rotate it, you can translate it, you can do whatever. That is not going to affect either your Lorentz, that is your special relativity, or your Galilean relativity. They will remain the same. But it's a very important point to keep in mind. Actually, it's true.
Is there any difference between how mass? Okay, so maybe how mass is defined in say Newtonian mechanics versus relativity because they are different in that sense. Like mass is a proportionality constant in.
Mass is one of those very interesting objects. So mass in school is defined as the inertial content of a body, which means nothing. Even today, to me, it means nothing, right? But however, Pound and Repka showed that inertial mass and gravitational mass are the same. So when you think of GR, then you can think of mass in that sense, right? By the amount of gravitational pull exerted by that object tells you what is the mass or inertial mass, which is the same as the gravitational mass of the body. For Einstein, mass is a geometric quantity. When you think of 4 vectors, mass is an invariance of some particular vector, of actually the energy 4 vector, okay? So you think of it as geometric. When you come to quantum field theory, you will think of mass as coming due to interactions of particles. So interaction of all particles with the Higgs field will give the mass to that object. As far as I am concerned, I think the question of mass is open. We still really don't know what mass is, okay? But that is philosophy. Factually, here, geometrically, in special theory of relativity, mass is an invariant of some particular 4 vector. Like how we wrote S squared is c squared t squared minus x squared minus y squared minus z squared. You can write m squared is equal to some object, okay, and therefore it has a geometric interpretation. That is how Einstein thought. I think that Einstein thought of mass, okay, as a geometric entity. Yeah.
Ma'am, while he is asking, that first person, he asked like any particle can travel faster than light in that medium, right?
Yeah.
That
Faster than light anywhere. For me, medium is not important, right? Is there a medium, special medium where you can travel faster than light?
Cherenkov radiation in nuclear.
No.
In Cherenkov radiation, we.
In Cherenkov radiation, the particle travels faster than the speed of light in that medium.
Yeah, that
But it
medium.
cannot travel faster than the speed of light in vacuum.
Okay.
Right? Nothing travels faster than the speed of light in vacuum. In the beginning itself, I said, whenever I talk about C, it is in vacuum. I am not talking about media. So what Cherenkov radiation is that if the velocity in water, for example, is 1 by 1.33, let's call it 0.6 times C, then the particle travels faster than 0.6 C, but never faster than C, okay? 0.6 is too small, but somebody can do 1 by 1.33 and tell me the answer, whatever it may. Sorry, my fractions are not my strong point. Okay, fine, but you understand, right? You cannot exceed speed of light in vacuum.